All right, so last video we were dealing a lot with breaking down equations involving delta S, or changes in entropy. And as you can remember, when I have a change of anything, a delta, this is going to be like the final minus initial, right? S final minus S initial, or just at two different points along the path, you may say something like S2 minus S1. The difference in entropy at those 2 points. Okay, now this is reminiscent of other quantities that we've seen changes in, like changes in pressure, changes in temperature, things like that. And you'll remember that for those quantities, we had to discuss for each one whether or not there was some sort of absolute scale, an absolute zero that we could actually reach. And so I drew something like this, where I have a little scale here, and this now is going to be entropy. And is there a zero? Well, you can see as I've drawn it, there is. So there's a 0 point down here at the end of our scale that defines zero entropy. So we kind of want to think about what that means. Whatever zero entropy means, it's going to have to fulfill both of our conceptualizations of what it is. So first of all, there's the old-fashioned physics idea of entropy, where it was first discovered, that it converts between temperature and energy. And so this concept of zero entropy has something to do with what's going on with the energy of the system. The other concept, or the other definition of entropy, is a measure of randomness or disorder that's in a system. So there's going to be some idea that at zero entropy, there's like zero disorder. So what we want is to come up with a definition for what zero entropy means that sort of takes into account both of those principles. And in fact, this isn't just a trivial thing that I say in passing. We spent a bit of time discussing 0 Kelvin on a temperature scale and 0 pressure on like a pressure scale. And this we're going to do quickly, but it's so important that it has its own law. Neither of those quantities, their 0 points didn't require a law. But with entropy, we do. We have a whole law just talking about how to define the 0 point of entropy. And that law, as we've briefly discussed, is the third law of thermodynamics. So in the modern formulation of thermodynamics, there are only 4 laws. 0, 1, 2, and 3, okay? And so this third law is the final law that we have to learn. A note in passing as we end these laws of thermodynamics. In theory, all of the rest of the subject can be derived from simply these 4 laws. Now, some of it requires like a practical application, and you have to maybe define new variables or new symbols in order to get all of the little equations that we've gotten. But I want you to understand that in theory, all of the little details and little equations and everything can be all condensed and collapsed back down to those 4 laws of thermodynamics. 0, 1, 2, 3, 4. I got it right that time, 4 fingers. Okay. So what is the third law of thermodynamics? It defines the 0 point. So here it is, simply. Entropy of a pure crystal at 0 Kelvin is 0. That's the law. Now, there's a couple questions regarding that. Why a pure crystal? So let me write that. Why pure crystal? Well, we know that this is going to have something to do with randomness, okay? And so the randomness is, in some sense, a measure of how much about the system I don't know. And I want to re-talk about something that I mentioned last week, which is the definition of what it means for a physicist to know something. When a physicist talks about knowing or not knowing a quantity, what they mean is they would like to know, so here's what it means. They would like to know the position and momentum of every single particle. So I'm going to start listing all the things that we want to know. Particle 1, we want to know its x-coordinate, its y-coordinate, and its z-coordinate, subscripts for particle 1. Then we want to know its momentum. Remember from tech physics that P means momentum. Px1, Py1, Pz1. So these are the 3 position coordinates and 3 momentum coordinates for one particle. Now we go x2, y2, and on and on. The list goes on and on and on because you can't even begin to imagine how many particles are, like, we've talked about how many are in a mole, right? So any macroscopic object, it has an insane number of particles in it. And so if we are demanding that zero entropy mean that we know the position, coordinates, and momentum in all directions of every single particle, then we have to have a definition like this, a pure crystal. That's because in a pure crystal, all of the atoms and molecules are in perfectly predefined locations. So there's no uncertainty as to their position. Other substances that aren't pure crystal, so other things like, I don't know, just random examples, grass, trees, asphalt, any other solids, those particles or those molecules can be arranged in slightly different ways and still make, like in the case of a tree, it still makes wood, right? You could have it like this or like this or like this. It doesn't quite care how the particles are arranged. It'll still be the same substance. Not pure crystal. Pure crystal, by the definition of what a crystal lattice is, it means that every particle has to be arranged in only one way. Even an impure crystal, that would fail. This definition is not talking about that. A crystal could be perfect with one defect. Well, that defect, we don't know about it. What is that defect? I can't predict it. But a perfect crystal, without even seeing it, I can go, yep, I theoretically know where every single particle is in that crystal. So that's why pure crystal. There's only one way it can be arranged. And then why 0 Kelvin? So this one should be intuitive to you. 0 Kelvin, because we also need to know the momentums. So if these particles have any energy, meaning that they're moving at all, even the slightest wiggle is still an uncertainty. Okay, it's still an unknown thing. So these particles can't even have the slightest wiggle in them. So what that means is the answer here, no motion at all. Now on Friday, a great point was brought up. Can we actually ever have zero entropy? Well, we've talked at length about the fact that we can't ever actually have 0 Kelvin. We can just get incredibly close. So this is the same thing. The definition of zero entropy involves 0 Kelvin, which isn't unreachable. So therefore, technically, perfect zero entropy is unreachable. Okay, we can't quite get there, but we can still define where the 0 point is in theory. Okay. Now, this means that we've fulfilled both of our intuitions about what entropy should be. First of all, we have maximum organization. Those particles in a perfect crystal are at 0 Kelvin, so they're not even moving, they're just sitting perfectly still, are as organized as they can possibly be. Think of this as being a deck of cards in new deck order, where maybe even the new deck has labeled on it the order that the cards come in, so you know everything. There's absolutely no question in your mind, no uncertainty about the randomness or the disorder in those cards. They are perfectly organized. The other intuition we had was that zero entropy should have something to do with energy, some link to energy. Well, notice that in this definition, if these particles are at 0 degree Kelvin in a perfect crystal and they're not moving, there is no energy in them. Okay, so these are just like little thinking points. So this is the definition of what zero entropy is, and we call it the third law of thermodynamics. That's how important it is in rounding out our entire picture of thermodynamics, because it may seem trivial, just set the 0 point, or maybe even just do this, but why do we need a law? It's because this is such a fundamental concept that we don't want to just be talking about changes, right? This could be a delta S, and that could be anywhere, and it could be any size, but if we're going to talk about absolute entropies, we need to know how far up the scale they've come. Okay, so that is the third law of thermodynamics. Okay, I'll be right back.